Picture this. Your 12-year-old builds a solar-powered weather station that feeds real environmental data to a global research network, then writes the Python script to analyze it. That's not some distant future. That's this weekend if you choose the right kit. I'm Chloe Miller, and today we're cutting through the noise to find STEM project kits that actually teach industry-standard tools like Arduino IDE, Python, and CAD software while delivering something tangible, working robots, renewable energy systems, data collection platforms that matter.
You're listening to the STEM Lab podcast. Quick note before we jump in. All the research, data, and writing in this episode come from our human authors who've tested this stuff in real-world conditions, but the voice you're hearing is AI-generated to make production sustainable. Just wanted to be upfront about that. If you're a regular listener here, thank you, seriously. If you're new, welcome. We release new episodes every Monday, Wednesday, and Friday, covering STEM kits, tools, and projects that actually teach kids useful engineering skills. Today, we're cutting through the noise around STEM project kits for 12-year-olds, specifically which ones teach real capability versus which ones end up as expensive shelf decoration. Let's get into it. The best STEM project kits for 12-year-olds bridge tinkering and real-world capability. At this age, kids transition from guided builds to open-ended engineering challenges. They're ready for kits that demand troubleshooting, iterative design, and genuine problem-solving. You'll want platforms that grow with them, support multiple programming languages, and connect to the tools they'll encounter in high school robotics clubs, maker spaces, and eventually STEM careers. The sweet spot? Kits that scaffold complexity without handholding, that fail gracefully so your kid learns to debug, and that produce something genuinely useful, not another dust-collecting gadget. Let's find the kit that turns curiosity into capability. Now, what should you actually look for in these kits? First up, progressive skill architecture and expandability. The best STEM project kits for 12-year-olds function as platforms, not endpoints. You're investing in a system that should accommodate skill growth over years, not weeks. Look for kits compatible with multiple programming environments, starting with visual block-based coding like Scratch or Blockly, but offering clear pathways to text-based languages like Python, C++, or JavaScript. Take LEGO Education's Spike Prime as an example. Kids begin with drag-and-drop Scratch blocks, then transition to Python on the same hardware without buying new equipment. That's genuine expandability. Check whether the kit supports third-party sensors, actuators, and modules. Can your 12-year-old add a soil moisture sensor, a servo motor, an OLED display? Open ecosystems like Arduino and Raspberry Pi excel here. You're not locked into proprietary expansion packs that cost 3 times what generic components would. Evaluate whether the kit's learning curve mirrors actual skill development. The first project should succeed in under an hour. The 10th project should challenge your kid for days. If a kit plateaus after 5 identical builds with minor variations, it's a toy masquerading as education. Next consideration, technical compatibility and infrastructure requirements. 12 is the age where you stop babying the tech stack. Your kid should learn to navigate real development environments, not dumbed-down walled gardens that teach nothing transferable. Check OS compatibility across Windows, Mac OS, Linux, and Chromebook. Many schools issue Chromebooks, so if the kit requires proprietary Windows-only software with no web-based alternative, you've just bought homework friction. Scrutinize offline versus cloud dependency. Kits that demand persistent internet connectivity teach kids that tools live elsewhere, controlled by corporations. Offline-capable platforms like Arduino IDE and Python IDE teach self-sufficiency. The Arduino Uno R3 runs entirely on your local machine. You own the toolchain. That matters.
Power requirements matter more than you'd think. Battery-only kits drain fast during intensive projects and generate e-waste. Wall adapter systems let kids run extended experiments. Think environmental monitoring that logs data for days. USB-powered devices offer flexibility, but check current draw. Underpowered USB ports cause maddening intermittent failures. For robotics kits, rechargeable lithium battery packs beat AA batteries economically and ecologically after about the third project. Connectivity isn't just about Wi-Fi. Does the kit support Bluetooth, I2C or SPI for sensor chains, GPIO pins for custom integrations? At 12, kids are ready to understand communication protocols. These aren't implementation details, they're foundational concepts for IoT, robotics, and embedded systems. Third thing to consider, concrete skill outcomes and career pathway alignment. Forget age ranges, demand skill outcomes. A good kit should articulate exactly what capabilities your child will gain. Programs autonomous navigation using ultrasonic sensors and proportional integral derivative control loops beats learns coding and robotics by miles. Look for kits that introduce industry-standard tools and workflows. Does the robotics kit use ROS concepts? Does the electronics kit teach circuit simulation in Tinkercad or Fritzing before physical builds? Does the data science kit introduce pandas data frames and matplotlib visualizations, actual Python libraries working professionals use daily? The best kits don't hide complexity behind proprietary abstractions, they scaffold it. A 12-year-old using Lego Spike Prime learns I2C communication, pulse width modulation for motor control, and sensor fusion, concepts that translate directly to career-level embedded systems work. That's not accidental. That's curriculum design that respects your kid's capacity. Assess whether the kit connects to real-world applications. Environmental monitoring kits that contribute to actual citizen science projects teach that engineering produces value beyond personal satisfaction. Renewable energy kits that power functional devices, LED lighting, phone chargers, aquaponics pumps, demonstrate that sustainable technology isn't theoretical. Your kids should finish projects thinking, I built something that works in the real world, not I completed the tutorial. Finally, durability, consumables, and total cost of ownership. Project-based learning means repeated use, failure, debugging, and rebuilding. Kits with fragile connectors, proprietary consumables, or components that break after 3 assemblies teach kids that tools are disposable. That's the opposite of what we need them to learn. Evaluate build quality honestly. Are the sensors industrial grade or toy grade? Can the microcontroller survive a shorted circuit with reverse polarity protection and current limiting, or does one wiring mistake brick $40 of electronics? Quality kits include redundant components for the most failure-prone parts. The Grove system uses keyed connectors that prevent miswiring, smart design that lets kids experiment without fear. Check subscription requirements. Many robotics kits now hide core functionality behind monthly cloud subscriptions for premium features, advanced lessons, or online simulators. That's a business model, not education. You're teaching your kid that capability is rented, not owned. Hard pass. Consumable costs matter. 3D printing kits burn filament, figure $20 per kilogram, with starter projects using 50 to 200 grams each. Electronics kits with breadboards and jumper wires cost almost nothing to expand, while proprietary sensor packs from big educational brands can run $30 to $60 per module. Calculate cost per project hour. A $200 kit that enables 100 hours of varied projects beats an $80 kit that's exhausted after 6 hours. Repairability is sustainability. Can your kid replace a burnt-out LED, swap a broken servo, or solder a new header pin? Or is the kit a monolithic sealed unit where one component failure means total replacement? Teaching kids to repair what they break isn't optional. It's central to engineering literacy. All right, let's get into our top picks. Starting with the LEGO Education Spike Prime Set. Check the show notes for a link to the current price. This delivers the most sophisticated brick-based engineering platform LEGO has ever shipped, combining their proven Technic building system with a 6-port intelligent hub running dual-core processors, a gyroscope, accelerometer, Bluetooth connectivity, and a 5x5 LED matrix. You're looking at genuinely capable hardware wrapped in LEGO's forgiving form factor. The hub's powered via rechargeable lithium-ion battery, around 8 hours runtime,
or continuous USB-C connection. You get over 500 pieces, including motors, distance sensors, force sensors, color sensors, and structural elements. Programming happens to the free Spike app on Windows, macOS, iPad, Android tablets, or Chromebook using Scratch-based visual programming or Python text coding. It operates offline after the initial app download and expands with all LEGO Technic components, plus limited third-party sensor compatibility.
What will your kid actually learn? Multi-threaded programming with parallel event handling, sensor fusion, proportional motor control, gyroscopic stabilization, object-oriented programming fundamentals in Python, mechanical advantage through gear ratios, structural engineering for mobile robots, rapid prototyping, and iterative design. These capabilities map directly to first LEGO League competitions and provide scaffolding toward advanced platforms like Vex or Arduino. The Python implementation is genuine. Your kid writes real Python 3 syntax, imports libraries, defines functions, and debugs code line by line. It's not Python-flavored blocks. The transition from Scratch to Python happens seamlessly within the same project. You can test sensor logic in Scratch, then rewrite it in Python to add complexity. That's pedagogically brilliant. What works well here? Dual programming pathways on identical hardware eliminate platform switching friction. The robust LEGO construction tolerates hundreds of rebuild cycles without wear. 6 programmable ports support complex multi-sensor robots from day one. Bluetooth connectivity enables wireless debugging. The hub's gyroscope and accelerometer unlock balance and stabilization projects like self-balancing robots and inclinometers. You get seamless expandability with hundreds of dollars in existing LEGO Technic parts most households already own. 0 consumables, 0 subscription fees, fully offline capable. Strong alignment with competition robotics. The trade-offs: the powered-up connector protocol limits third-party sensor compatibility. You can't easily add generic Arduino sensors without adapters. The hub's storage constrains large Python programs with extensive libraries. No native Wi-Fi, Bluetooth only, which prevents direct IoT applications without tethering to a computer. The Spike app's Python editor lacks advanced IDE features like pip package management and robust debugging tools. Price point usually runs around $360 to $380, which makes this a significant investment compared to bare Arduino kits. Brick-based construction, while versatile, can't achieve the precision or speed of purpose-built robot chassis for competitive applications. Next up, MakeBlock MBot 2 Robot Kit. Check the show notes for the current price. This positions itself as the bridge between toy robots and serious engineering platforms. It ships with an ESP32-based controller, ultrasonic sensor, line-following sensor, encoders on both motors, Wi-Fi and Bluetooth radios, and 3-stage programming from MBlock, a Scratch fork, to Python to Arduino C++. It's a deliberately designed capability ladder. You get an ESP32 dual-core processor running at 240 MHz with integrated Wi-Fi and Bluetooth. Power comes from 3 rechargeable lithium batteries, charger included, or 6 AA batteries. The aluminum chassis has 4 ports for MakeBlock ecosystem sensors, plus an onboard buzzer, RGB LED, light sensor, and gyroscope. Programming happens via MBlock 5 software on Windows, macOS, Chrome OS, iOS, or Android. It operates offline after cloud assets are cached and works with Arduino IDE via the MakeBlock library. You also get a wireless dongle for computer control and compatibility with over 60 MakeBlock sensors and modules. Skill outcomes include Wi-Fi programming and IoT fundamentals covering MQTT and HTTP requests, PID motor control using encoder feedback, obstacle avoidance algorithms, maze-solving logic, remote operation protocols, Arduino library integration, ESP32 microcontroller architecture understanding, lithium-ion battery management, and wireless debugging. This prepares kids for intermediate platforms like ESP32.cam or larger MakeBlock projects.
The ESP32 chip is the same one powering thousands of commercial IoT devices. Your 12-year-old isn't learning a proprietary system. They're learning a microcontroller that costs less than $10 and drives everything from smart home sensors to agricultural automation. That's transferable knowledge. MBlock's AI module offers age-appropriate machine learning introductions through computer vision via webcam and speech recognition without requiring kids to understand neural network mathematics. They train image classifiers, then deploy them to robot behaviors. It's supervised learning made tangible. What works? ESP32 Wi-Fi enables genuine IoT projects like web-based robot control and sensor data logging to cloud platforms. 3-tier programming supports 3+ years of skill growth without hardware replacement. Encoder-equipped motors teach closed-loop control concepts missing from most beginner robots. The rechargeable battery system eliminates AA waste and reduces long-term operating costs. The aluminum chassis and metal gear motors survive rougher handling than plastic competitors. Strong make-block ecosystem offers clear upgrade paths. Onboard sensors mean functional robots without add-on purchases, compatible with Arduino IDE and standard Arduino libraries for advanced users.
The trade-offs. MBlock software requires cloud connectivity for initial setup and periodic updates, limiting fully offline use. The connectors are MakeBlock proprietary. Generic Grove or Gravity sensors need adapter cables. Documentation assumes some prior robotics experience, so complete beginners may struggle with advanced tutorials. Battery access involves screws and wire management, making swaps clumsier than tool-free designs. Wi-Fi range limits to around 30 feet from router in typical home construction. Python implementation in MBlock is MicroPython, a subset, not full CPython. Some libraries are unavailable. Price typically runs around $160 to $180, sitting in a crowded middle tier. Third pick, Elegoo Mars 3 Pro 4K Resin 3D printer. Wait, a 3D printer and a project kit list? Absolutely! Check the show notes for the current price. This isn't a project kit itself, it's a project multiplier that transforms every other STEM activity into custom engineering. 12-year-olds designing their own robot grippers, sensor enclosures, wind turbine blades, or replacement parts in Tinkercad or Fusion 360, then printing them overnight? That's when STEM learning becomes making. You get a build volume of about 5.6 by 3.5 by 6.9 inches, a 4K monochrome LCD with 35-micron precision, UV LED light source at 405 nanometers, heated build platform, and around 2.5-hour print time for a 50mm object. It uses Qi2 box slicing software, free, works on Windows, macOS, and Linux. File transfer happens via USB thumb drive, no Wi-Fi. It requires 405 nanometer resin, which is third-party compatible, plus 99% isopropyl alcohol for post-processing, a UV curing station, nitrile gloves, and safety glasses. It produces resin odors, so you'll want a ventilated space. Skills learned include 3D CAD design iteration and file preparation, slicing software mastery with support generation and exposure calibration, comparing subtractive versus additive manufacturing, material science covering resin chemistry and photopolymerization, dimensional accuracy and tolerance specification, post-processing workflow development, and chemical safety protocols. These capabilities parallel professional rapid prototyping workflows in product design, medical devices, and aerospace. Resin printing's precision exceeds filament-based FDM printers by an order of magnitude. Your kid can print functional gears with 0.1mm tolerances, watertight enclosures for electronics, or prosthetic hand components. That's engineering at a scale FDM can't match. But, and this is critical, resin printing demands real chemical safety practices. Uncured resin is a skin sensitizer and respiratory irritant. 12-year-olds can absolutely handle this responsibility, but it requires setup, dedicated ventilation, PPE discipline, proper waste disposal. This isn't a dining table project.
The build volume limits projects to smaller than a grapefruit, but that encompasses 90% of STEM kit applications: custom sensor mounts, robot wheels, enclosures, experimental fixtures. Pair this with renewable energy kits, print custom turbine blade profiles to test aerodynamic efficiency, or prototype solar tracker mechanisms. What works? 35-micron precision enables functional mechanical assemblies impossible with entry-level FDM printers. Fast print times, most projects 1 to 3 hours, support same-day iteration cycles. Third-party resin compatibility with water-washable, plant-based, and ABS-like formulations reduces consumable costs. Chi2 Box Slicer is fully featured and free with active community support. Build platform leveling simplified. Heated platform improves layer adhesion. Monochrome LCD screen lasts around 2,000 hours, 2 to 3 years typical use, versus 400 to 800 hours for older RGB screens. You can create custom solutions for other STEM projects rather than forcing compromises with off-the-shelf parts. The trade-offs? Resin handling requires strict safety protocols. Ventilation, PPE, waste disposal, not appropriate for unsupervised use at this age. Consumable costs add up. Resin around $25 to $35 per kilogram, IPA $15 to $25 per gallon, replacement film $12 to $18 every 10 to 30 prints, LCD screen $65 every 2,000 hours. Learning curve steeper than FDM. First prints often fail due to support placement or calibration issues. Prints require 10 to 20 minutes of post-processing per object. No Wi-Fi or network connectivity. File transfer only via USB drive adds friction. Resin odors persist despite low odor marketing. Ventilation mandatory. Build volume constrains larger projects. Won't replace need for FDM printer for big parts. Fourth pick, Adafruit Clue and Environment Sensor Bundle. Check the show notes for the current price. The Adafruit Clue might be the most underrated platform in youth STEM education. A matchbox-sized board crammed with 9 onboard sensors, a color TFT display, and the horsepower to run CircuitPython, Arduino, or MakeCode. Add Adafruit's curated environmental sensor bundle covering air quality, VOC and ECO2, CO2, and particulate matter, and your 12-year-old has a portable environmental research lab that collects publication-quality data. You get a Nordic microcontroller with 1 megabyte flash and 256 kilobytes RAM. Integrated sensors include accelerometer, gyroscope, magnetometer, temperature, humidity, pressure, light, color, proximity, microphone, and speaker. The 1.3-inch color display runs at 240 by 240 resolution. It supports Bluetooth 5.0 low energy. 3 programming options: CircuitPython for beginner-friendly Python, Arduino IDE for C++, or Microsoft MakeCode for blocks. Power via USB-C or 400 mAh battery connector, battery sold separately. It works with Windows, Mac OS, Linux, and Chromebook via drag-and-drop file programming with no drivers needed. Skills include environmental data acquisition and quality control, sensor calibration and uncertainty quantification, time series data logging and visualization with CSC export, I2C communication protocol and sensor addressing, Bluetooth low energy data streaming, power optimized code for battery operation, citizen science data contribution to platforms like Purple Air, and Python data frames and statistical analysis. This aligns with high school AP environmental science curriculum and undergraduate atmospheric science lab skills. The air quality sensor measures total volatile organic compound levels. Your kid can map air pollution patterns around their school, test whether houseplants actually improve indoor air quality. Spoiler, the data is complicated. Or correlate traffic density with particulate matter. That's authentic environmental science. The CO2 sensor enables classroom ventilation studies, which is timely given post-pandemic attention to indoor air quality. These aren't toy sensors. These are the same MEMS devices in commercial air quality monitors. CircuitPython's save file code runs instantly workflow eliminates the compile, upload, wait cycle that frustrates beginners. Your kid edits code in any text editor, hits save, and sees results in under 2 seconds. That feedback loop changes everything. Libraries for every sensor come pre-written. Want to add a GPS module for mobile air quality mapping? 3 lines of code. The Clue pairs beautifully with citizen science projects. Join Purple Air's sensor network, contribute to NASA's Globe Observer program, or design a hyper-local environmental monitoring project for your neighborhood. Your kid learns that data collection serves a purpose beyond grades. What works? 9 onboard sensors eliminate what do I buy first paralysis. Everything included to start experiments immediately. CircuitPython's beginner-friendly syntax and instant feedback lower frustration threshold. Drag-and-drop file programming works on any OS without driver installation, critical for Chromebook users. Color display enables on-device data visualization without tethering to computer. Bluetooth Low Energy supports mobile app development for wireless monitoring. Extensive Adafruit tutorial library provides project ideas and starter code. Battery-powered operation enables field deployment like park air quality transects or hiking trail environmental gradients. Community support via Adafruit Discord responds to questions within hours. Reasonably priced, Clue around $40 to $50, sensor bundle $80 to $100 for laboratory-grade sensors. The trade-offs. The microcontroller's RAM limits data logging to around 8,000 readings before requiring SD card expansion, which isn't included. CircuitPython's subset lacks some advanced libraries available in full C Python, no NumPy, limited threading. Small form factor makes breadboarding awkward, better suited to sensor chains than complex circuits. No Wi-Fi. Bluetooth only means cloud data sync requires phone or computer intermediary. The display draws significant power, battery life around 6 to 8 hours with display active, necessitating external battery pack for day-long fieldwork. Sensor bundle requires individual I2C addressing configuration, not plug-and-play for complete beginners. Air quality readings are relative index values, not absolute concentrations, requiring careful interpretation. Fifth pick, Arduino Engineering Kit R2. Check the show notes for the current price. This represents Arduino's first serious swing at comprehensive project-based curricula, delivering 3 sophisticated builds: self-balancing motorcycle, rover with drawing mechanism, and motorized whiteboard camera, alongside a collegiate-level engineering course covering control theory, mechanical systems, and computer vision fundamentals. This is Arduino acknowledging that hardware without pedagogy is just parts. You get an Arduino Nano with Raspberry Pi dual-core processor at 133 MHz, Wi-Fi, and Bluetooth. The motor carrier includes H-bridge drivers, IMU, and battery management. You also get a webcam with computer vision library for color blob detection and line following. Over 200 parts, including structural aluminum, motors, wheels, servos, batteries, and sensors. Arduino Cloud subscription included for 1 year. Programming via Arduino IDE or Arduino Web Editor on Windows, Mac OS, Chromebook, or Linux. Online curriculum with over 10 hours of video instruction and simulations. Skills include PID control loop design and tuning, system identification and transfer function modeling, inverted pendulum stabilization, fundamental control theory problem in aerospace and robotics, odometry and dead reckoning for mobile robots, computer vision color blob detection, Wi-Fi-based remote operation, mechanical design for motion transmission with gear ratios and belt drives, and simulation before physical builds. This is direct preparation for university engineering coursework and professional robotics platforms. The self-balancing motorcycle isn't a gimmick, it's a vertical inverted pendulum, one of the canonical control theory challenges. Your kid implements PID controllers that adjust wheel velocity over 100 times per second to maintain balance, then iteratively tunes gains while observing oscillation, overshoot, and steady-state error. That's sophomore-level mechanical engineering content, scaffolded for a 12-year-old. The included curriculum uses simulation software to model the system before building it, teaching the simulate before fabricate workflow that saves professional engineers millions. The Arduino Cloud integration enables remote robot control via web dashboard, teaching REST API concepts and client-server architecture without drowning kids in networking minutia. Your kid builds a mobile robot, then accesses it from their phone browser while it's 3 states away at grandma's house. That's both technically impressive and pedagogically valuable. They're learning distributed systems by doing, not memorizing. What works? Curriculum-embedded approach teaches engineering theory alongside practical builds, understanding why the code works.
PID control loop implementation transfers directly to drones, CNC machines, 3D printers, and autonomous vehicles. Simulation exercises introduce industry-standard tools before high school. The dual-core processor runs real-time control loops without timing issues plaguing single-core designs. Arduino Cloud subscription simplifies remote monitoring without managing MQTT brokers or web servers manually. Mechanical builds robust enough to survive weeks of testing, tuning, and inevitable crashes. Webcam-based computer vision projects cost-effective compared to dedicated cameras. All components remain useful after completing curriculum. Reuse sensors and motors for custom projects.
The trade-offs. Price usually runs around $200 to $230, steep for families who already own Arduino boards, essentially paying for curriculum and bundling convenience. Curriculum simulation dependency creates friction, licenses expensive after student version expires, alternatives less user-friendly. Documentation assumes comfortable math literacy, including algebra and basic calculus concepts. Struggling math students may need supplementary support. Web editor requirement for some curriculum sections means partial cloud dependency, despite IDE capability. Motor carrier has only 2 motor channels, limits robot designs to 2-wheel differential drive or single-axis control. Curriculum lacks clear progression to next steps, completes 3 projects, then stops without roadmap to intermediate challenges. The processor's Arduino core is younger and less mature than others, causing occasional library compatibility issues with legacy Arduino code. Final pick, Thames and Cosmos Solar-Powered Innovations Kit. Check the show notes for the current price. This ditches the Arduino and focuses on pure renewable energy engineering, photovoltaic fundamentals, mechanical energy storage, solar tracking mechanisms, and efficiency optimization through over 50 build and test experiments. This kit acknowledges that not every 12-year-old wants to code. Some want to build physical systems that harness energy from the sun, and that's equally valid STEM. You get a polycrystalline solar panel rated at 6 volts and 200 milliamps maximum output, gold cap supercapacitor energy storage, analog voltmeter and ammeter for electrical measurement, gear motors with multiple ratios, and structural components for solar car, boat, helicopter, water pump, Ferris wheel, and experimental test rigs. No microcontrollers, no programming, no batteries required. 100% solar-powered operation. The 64-page full-color manual includes experiment instructions and renewable energy science background. It's compatible with other Thames and Cosmos solar kits for expanded projects. Skills include photovoltaic energy conversion efficiency measurement, series versus parallel circuit configurations and their voltage current trade-offs, energy storage systems comparison with capacitor versus battery discharge curves, mechanical advantage through gear ratio selection, solar angle optimization and tracking mechanism design, load matching for maximum power, efficiency limitations and real-world losses, and experimental design with variable isolation. These are foundational concepts for energy engineering, electrical engineering, and environmental science without requiring programming skills. The gold cap supercapacitor teaches energy storage physics differently than chemical batteries. It charges in seconds, discharges completely without damage, and visibly demonstrates energy density limitations. Your kid discovers why their solar car loses power immediately when you block the panel with capacitor storage, but runs longer after sunlight ends with battery storage from a different kit. That's materials science made tactile. The manual's experiments scaffold genuine scientific inquiry, build the solar car, measure its speed in direct sunlight. Now, add a 2-to-1 gear reduction and measure again. Calculate the efficiency change. Hypothesize why speed decreased, but hill climbing ability increased. That's engineering method, not instructions to follow, but problems to solve. The kit's analog meters, not digital, force kids to interpolate needle positions and calculate percentage uncertainties, building measurement literacy digital displays obscure. The solar panel is large enough, around 6 by 4 inches, to produce meaningful current, enough to drive motors under load, charge capacitors in seconds, and demonstrate the difference between morning, noon, and evening solar angles. You're working with solar flux densities that model real photovoltaic engineering, not token power. What works? Zero screen time, zero coding. Appeals to hands-on and kinesthetic learners underserved by software-heavy STEM kits. 50-plus experiments provide months of project variety. Solar panel and supercapacitor remain useful indefinitely. No batteries to corrode, no consumables to replace. Analog meters teach measurement skills and uncertainty quantification, lost in digital display culture. Mechanical builds complement rather than compete with electronics-focused kits. Manual's renewable energy content directly addresses climate science and energy transition topics. Immediate sensory feedback. Motor speed changes with cloud cover. Gear whine varies with load. Teaches cause-effect without abstraction layers. Compatible with renewable energy science fair projects and citizen science energy audits.
The trade-offs are geographic limitations make solar kits genuinely frustrating in Seattle winters or high-latitude locations with limited winter sunlight. No expandability to data logging or electronic measurement, can't record efficiency curves over time without external equipment. Manual's 50 experiments vary wildly in depth. Some offer rich investigation. Others feel like build this, observe that, without analysis. Structural components less durable than Lego. Plastic axles strip after repeated assembly and disassembly. Solar panel fragile if dropped. No protective carrying case included. Performance disappoints on cloudy days or indoors, needs direct sun or very bright artificial light. Voltmeter and ammeter accuracy adequate for comparative measurements, but plus or minus 10% error limits precision experiments. Zero programming means kit doesn't integrate into microcontroller learning paths, functions as parallel track, not stepping stone. Now, let's tackle some frequently asked questions. What programming languages should 12-year-olds learn with STEM project kits? Your 12-year-old is at the perfect inflection point to transition from visual block coding to text-based programming. Start with Scratch or Blockly to establish programming logic, loops, conditionals, functions, events without syntax frustration. Then pivot to Python within 3 to 6 months. Python dominates data science, machine learning, web development, and embedded systems through MicroPython and CircuitPython on microcontrollers. It's the most versatile first text language. Once comfortable with Python fundamentals, introduce Arduino C++ for robotics and hardware projects where performance matters. The dual language approach, Python for high-level logic and data processing, C++ for time-critical embedded control, mirrors professional engineering workflows. Avoid JavaScript initially, despite its web ubiquity. Its quirky syntax and asynchronous patterns confuse beginners. Are STEM project kits at age 12 worth the investment compared to online coding courses? Physical project kits and online coding courses serve complementary but non-interchangeable roles. Kits teach systems thinking, debugging physical failures, mechanical constraints, sensor noise, power limitations, and the humbling reality that code must interface with messy reality. Online courses teach syntax, algorithms, and software architecture in sterile environments where variables never experience electromagnetic interference and loops always execute at predictable speeds. Your 12-year-old needs both. The kid who learns Python exclusively through screen-based courses often struggles when their first hardware project fails due to a loose wire. They've mastered syntax, but not troubleshooting physical systems. Conversely, the kid who only tinkers with kits may build impressive robots but lacks the computer science foundations to write efficient algorithms or understand complexity analysis. Optimal strategy: use project kits as the motivating application, supplement with focused online coursework to deepen specific concepts like data structures, version control, and testing frameworks. The kit investment pays dividends in sustained motivation. Building something tangible beats abstract exercises for most 12-year-olds' engagement. Supervision requirements vary by project hazard profile, not age. 12-year-olds can independently manage most electronics projects, Arduino breadboarding, coding, sensor integration, after initial safety training on polarity, short circuits, and current limits. They should handle low-voltage soldering, supervised initially, by this age. The skill is foundational, and the risks, minor burns, no fire hazard with low wattage irons, are manageable with proper technique. Projects requiring supervision at age 12. Resin 3D printing due to uncured resin skin sensitization, power tools beyond handheld screwdrivers, high current circuits involving wall voltage or over 2 amps DC, and chemical handling like acid-base etching or strong cleaning agents. The standard should be demonstrated competence, not arbitrary age limits. The 12-year-old who independently troubleshoots a shorted Arduino by methodically checking connections and reviewing datasheets has earned trust. The one who repeatedly blames broken equipment instead of debugging needs more guidance. Build safety culture, not fear. Explain why isopropyl alcohol requires ventilation, why lithium batteries shouldn't be punctured, why desoldering produces fumes. Informed autonomy beats anxious hovering. Should we buy one comprehensive STEM kit or multiple specialized kits? Start with one platform-style kit, Arduino, Raspberry Pi, Lego Spike, that supports 6+ months of progressive projects. Then add specialized kits only after your child demonstrates sustained engagement and bumps against the platform's limitations. The comprehensive kit first approach prevents shiny object syndrome, where shelves fill with half-used kits that never integrated. A quality platform, like the Spike Prime or MBOT 2, offers sufficient complexity and expandability to teach fundamental concepts: programming logic, sensor integration, mechanical systems, debugging methodology. Once your 12-year-old exhausts the platform's built-in projects and starts designing custom applications, I want to build an automated plant watering system with soil sensors. That's the signal to invest in specialized expansion: environmental sensor kits, 3D printer for custom parts, renewable energy modules. The specialized additions amplify rather than replace the core platform. Exception: if your kid shows singular obsessive interest in a narrow domain like renewable energy, computer vision, or CNC fabrication, lean into that passion with specialized gear immediately. Sustained motivation trumps well-rounded curriculum. One kid deep into solar engineering builds more skills than 3 kids surface sampling every STEM domain. Here's the verdict. The best STEM project kits for 12-year-olds don't merely fill time, they build transferable technical capability using tools and platforms your kid will encounter in high school robotics clubs, college engineering labs, and eventually professional work. You're choosing between scaffolded complexity that grows with your child, Spike Prime, MBOT 2, Arduino Engineering Kit, versus specialized deep dives that develop domain mastery, Resin 3D printing for mechanical design, Clue for environmental data science, TEMS and Cosmos for renewable energy fundamentals. Both paths work. The former creates generalists prepared for interdisciplinary challenges. The latter cultivates specialists who understand their domain deeply enough to innovate within it. Choose the kit that aligns with your 12-year-old's learning style and your household's capacity to support the infrastructure each requires. The Lego Spike needs desk space and tolerance for scattered bricks. The resin printer demands ventilation and chemical safety discipline. The Clue Environment Bundle assumes willingness to spend weekends collecting field data. All 6 options covered here teach authentic engineering skills, use industry-standard tools, and avoid the subscription trap business models that teach kids to rent capability instead of own it.
Your kid will remember the weekend they debugged a stubborn sensor fusion algorithm, or printed the perfect gear ratio after 5 iterations, or mapped hyper-local pollution patterns that contradicted official monitoring data. That's not STEM education, that's engineering identity forming in real time. Pick the kit that gives them space to fail, iterate, and surprise themselves with what they can build. Then step back and let them build it. That wraps this episode of the STEM Lab podcast. Thanks for listening all the way through. We release new episodes every Monday, Wednesday, and Friday. Same deep dives, same honest breakdowns, no fluff. If this was useful, I'd really appreciate it if you'd leave a 5-star rating and maybe write a quick review. It's genuinely the main way new listeners find the show, and it helps other parents and educators discover these resources. And hey, if you haven't already, subscribe or follow so you get notified the second new episodes drop. Appreciate you being here. Talk soon.